Our next presenter is Magdal Gombrink. Magdal studied exploration geophysics at the University of Pretoria in South Africa, culminating in a PhD on the modeling of time-domain electromagnetic data. She's been involved on contract basis in groundwater exploration, mineral exploration, and engineering geophysics since 1996. She has lectured at the University of Pretoria for 4 years and has spent another 4.5 years working for Geotech. In 2010, she moved to Canada and together with Willem Botha started Tau Geophysics Consultants based in Calgary. She started consulting to NRG a couple of years ago, getting involved in the design and launch of the Excite helicopter EM system. And currently, she's acting as data processing manager for NRG and still enjoys unraveling the mysteries of time domain EM. And today, Magdal is going to talk about synthetic data as control for processing full waveform TEM data. Take it away, Magdal.
Thank you, Asbjørn, and thank you for everyone showing up here. It's always nice to talk to some people and not just chairs. So my talk is kind of a prequel to USense. My interest is more in processing of data and really making sure that when data gets to the point of being inverted and going through all the fancy things that these guys do with the data to make sure that they have the best possible version of data to work with. So I became interested in photography about 20 years ago. And although my passion was for photographing nature and wildlife, my mom was very excited at the prospect of having a photographer in the family because I could now do soft focus when doing portraits of our family events. And this was important as her wrinkles were starting to show up. And as humans, we are strongly influenced by visual presentations, and we also seem to evaluate images based strongly on their aesthetic value. And why not? Would you prefer to look at this portrait when you could have that as an option? And even if it's a real privilege to catch 5 cheetahs in one frame, why not make the moment even more memorable? To have a shot like that. And then finally, who of you would prefer to work with that profile when you can have that one? What could possibly go wrong? So photography and airborne EM data acquisition have shown similar trends over the last few decades, moving from analog to digital and then to overwhelming quantities of digital information. A trend that follows this technological evolution is that the contribution of processing or subjective human input to the final product, be it your photos or your airborne EM data, has been steadily increasing. And we have to remember that with great power comes great responsibility. So for this discussion, I'd like to divide the modern airborne acquisition and processing workflow into 3 parts, because we used to have acquisition and then processing, but these things have really become one process now with 3 phases. So we're looking at recording data, correcting data, and filtering data. And I'll explain these using the relatively new Excite system as example, as this is what I've been working with in the last 2 years and I'm currently the most familiar with. The more data you record, the more flexibility and options you have in the rest of the workflow. And the limitations today for recording data are determined mostly by data storage and software capabilities of dealing with the data. The Excite system records about 6,250 data points per full cycle, compared to a few years ago when you would get 20 channels, or 6 or 7 or 30 channels from a system. Data corrections are required to isolate the Earth response from the measured response, because the measured response would include system response, motion, and other types of signal that are not related to geology, and we have to do the best we can to reduce the data to only contain geological signal. Then we come to filters. Filtering are done for different reasons and are dependent on what the data will be used for. 3 requirements that I've come across are to attract investors' attention. And for this, you need significant aesthetic appeal. And I kid you not, I have had clients that, or contractors, consultants that send data back to me and say, please, we need to get this out on a press release tomorrow. It has to look better. So there's a definite market for that. You also would want to identify targets for follow-up. For that, you normally want to highlight your anomaly amplitudes relative to noise. And then when you come to the modeling and inversion, like Yusen and Andrea is working with the intent of drilling targets, you really want the highest numerical accuracy from your data. So corrections are system dependent and therefore often developed in-house and can have intellectual property implications. But very few exploration geophysicists would be confronted with these procedures, although understanding that corrections are applied and can lead to different results in data is really important if something does not add up in a survey. Filtering of data, though, is optional. That's system independent, but goal dependent, and a part of the workflow that I believe exploration geophysicists should take more control over, as the best filtering choices are determined by your specific survey goals in the end. Filtering changes data. And we have to ask at which point are we making it worse instead of better. So I used the following method to quantify effect of filters. I started by generating a synthetic full waveform data set with decay constants ranging from 0.01 to 10 milliseconds over a range of plate models. The next step was to obtain realistic noise samples. I used two for this study. The first was acquired at high altitude during an approaching thunderstorm. You'll see that at the top, and I'll reference this as the high noise sample. The second one was acquired under calm optimum survey conditions in the same area, referenced as the low noise sample. I then added these to the synthetic models and applied the standard corrections and processed the data until 32 gated channels were extracted for each model. Examples here are shown here are the 400 by 400 meter and 200 by 200 meter horizontal plates with decay constants equal to 1 and 5 milliseconds respectively. I've done quite a few more models, but I'll only focus on a few for this presentation. So there's a high noise example. This is the high noise example, and two highlighted stations will be referred to later when I talk more about quantifying the errors. So that's in the middle of the anomaly and just off the side. In this slide, the same models are shown, the difference being that the low noise samples were added here instead of high noise. And we'll look at those stations again later. At this point, I could start to apply filters and quantify the effects it had on the data. I wanted to use an error estimate that could be used to compare results from different models and channels, even though the amplitudes vary over several decades. So my solution was to use a filter error fraction defined as the standard deviation of the profile of the filtered profile data divided by the standard deviation of the unfiltered profile data. Both standard deviations are calculated over 300 points and relative to the model data without any noise added. This error estimate has the property that if the error fraction is less than 1, it means the filter data are a better approximation to the model than the unfiltered data. An error fraction larger than 1 implies that the filter data gives a worse approximation to the model data. I evaluated 7 filters in total. 3 were applied to the full waveform data in time series format before gating, while the 4 spatial filters were applied to data after gating along profiles. So one thing to note here is that this is one of the differences with recording full waveform data, is that we have the ability to, in post-processing, apply filters in the time series data. If you don't record the stream data, that is normally done during the acquisition process, and it's hardwired and you can't back and make any changes to that. So the first is a despiking filter. It's designed to remove spheric noise. In the small panel on the left, the black graph is showing the transmitter current, and the blue is showing data that's been recorded. And there are 2 spheric events that you can see there. And it's important to notice that not the whole decay is affected. These spherics are very sharp events. And this filter is designed to only remove that part of the decay that's affected by the spheric and keep the rest of the decay and use that data. So you can see the filter applied on the profiles. The spikes are taken out, and this is the low noise example. Here we have a high noise example. In this rather extreme case, the despiking filter does not remove all the noise because the spikes are so close to each other that it's hard to separate them from the background. But looking at the highlighted stations, again, we can look at the error estimates for each channel at these stations. So I'm showing the area that's larger than 1. That means that the filter would have made the data worse. There was very little change to the low noise data in blue, as expected. The high noise data had 3 channels where errors were increased, but in general the filter improved the accuracy of the data. To do a broader comparison, I averaged the error fraction over all the channels, so there is now only one number per station to look at and compare between the different models. These are displayed on the graph comparing 2 stations over 8 models. The low noise examples are at the top and the high noise examples are at the bottom. For all models except 2, the error is reduced after applying the despiking filter. The 2 examples with increased noise were found to be anomaly peaks so sharp that the algorithm actually picked these as spikes. These were 5 millisecond decay constant models picked right at the anomaly peaks. And I think it's unlikely that field data with overburden responses added would generate such sharp peaks, but the filter parameters can of course be adjusted as well to be less sensitive. Next up is a low-pass finite impulse response filter. I used 5, 10, and 15 kilohertz as cutoffs and first applied 5, 10, and 15th order filters. These do not show dramatic effects on the profile data, as most of the spatial noise comes from the much lower coil movement frequencies. Looking at that one station, you will see the error fractions for the 5th, 10th, and 15th order filters. These relate to 6, 11th, and 16 points each used, and you'll see quite large errors were introduced by the even point filters. So I substituted them with uneven point or even order filters. And now the noise levels came down, or the errors came down. This worked much better and reducing errors on this model instead of increasing it. So it's important to use symmetric filters. It's the lesson I learned from this one. So looking at the effect of filters in all the models, summarizing that, we see that the errors are generally reduced again. We have one anomaly. This time it's a smaller, weakest conductor which has the faster decay and was affected most in the low noise case. For high noise, the data was still improved. The last of the time series filters is what I call a variable width average. It uses exactly the same concept as gating schemes, where later channels are averaged over more points than earlier channels. The only difference is that all values are kept and not just a single averaged point. We can see some improvements on these high noise profiles, and looking at one station again. This filter generally does well, but on the 400 by 400 meter 5 millisecond model, we have errors in the late channels. This is the most conductive model with the highest amplitudes, and it turns out that linear averaging over the late times does not approximate the exponential decay properly, resulting in these errors. Just zooming in, anomaly amplitudes are still high in the late time for this model, and the filter that we applied show consistent shifts that's caused by this linear averaging, and summing that up over the whole model would add a large standard deviation, adds up to a large standard deviation. So comparing this filter with the previous for all models, as to the despiking filter as well, in orange, we see that it's quite effective on high noise data, and it's also the most effective of the 3 time series filters. So remembering that the high noise data are shown at the bottom, and you can see everywhere that we have values less than 1, we've actually improved the data by running this filter. So looking at the spatial filters, I've compared 4 types, and these are ones that you might be more familiar with, and I've specifically used filters that you would be familiar with, because the intent is that people working with the data now would get this in a more unfiltered version and be able to apply your own filters. But it's also important to know what happens with the data when it does get filtered. So I've compared the standard low-pass filter, a straight stacking or averaging filter, the nonlinear filter, and the Savitsky-Golay polynomial fit filter. The widths for each of these were varied from 21 to 201 fiducials, which translates to 10 and 100 meter respectively with the example data. So this is something else to notice with the full waveform data. We now have information every half a meter. So that's very densely sampled. This image shows a profile view of the 4 filters applied to one of the models with filter width of 50 fiducials or 25 meters. And at first sight, the nonlinear filter seems like a clear winner. Here we have the same filters applied to a more conductive model with low noise added, and in this case, some distortion in the nonlinear data is noticeable. So we'll look at the same error fractions again. This is the low-pass filter. And we can see that the low-pass filter really only improves accuracy for 6 out of the 16 cases evaluated, and racking up error fractions of up to 1,000 in the worst-case scenarios. Remember that the maximum filter width here is 100 meters, while the target widths are 200 and 400 meters respectively. So this is not a severe filter. The averaging filter does even worse. Only 3 cases out of the 16 shows improvement for widths more than 50 meters. The nonlinear filter does a great job of aesthetically smoothing the data, but can introduce very large errors very quickly. 20 fits are about the maximum width that can be justified for these models. The Savitsky-Golay is a polynomial fitting filter, and this one actually performs the best, benefiting the high noise data, but mostly still increasing error in the low noise examples. So over here I've added everything together to try and get a final comparison of all the different models. Data with low noise levels are very easily rendered less accurate when applying spatial filters, while even high noise data can be made worse if the filters are not used appropriately. So I have to note that these examples were all plate anomalies, and of course working in a layered earth environment, the data could tolerate more filtering without these detrimental effects. But then I had to ask, can we do better? The variable width averaging filter is the most effective time series because the filters are based on the data properties. Steep slopes and high amplitudes gets filtered less, while late time and gradual slopes and low amplitudes are filtered more. So if you look at my paper, I kind of stopped here because I ran out of time. But developing filters that apply a similar principle in the space domain based on data amplitudes and spatial curvatures is something that I wanted to look at, and I did get time to do that in the meantime. And this led to what I like to call the MOHAV, or the mother of all filters. So MOHAV is now a data adaptive variable width low-pass filter, the width which is based on curvature, and incorporating a few scaling and normalization factors. So applied to the same data sets with a variable width allowed to vary between 20 and 200, I get the following results. So the green line added to the rest is now the error introduced by this filter to the data. This filter gives error levels consistent with the lowest width low-pass filter, as that is the filter width that was applied over the anomaly. And we get the same for the high noise case. So just showing this on a example of real data. At the top, we have the unfiltered data. In the second panel, there's a 50 fiducial low-pass filter that honors the shape of the sharp anomaly, but noise remains visible on the rest of the profiles. You can push the low-pass filter width up to 400, which is very effective for removing the most noise, but severely compromises the shape of the sharp anomaly. And that's where we introduce errors that gets translated to all the inversions and further modeling of data. The MOA filter in the bottom applies short filter width to the sharp anomaly, honoring its shape, yet also removes most of the visible noise on the rest of the profiles. So in conclusion, recording of stream data on modern airborne EM systems allows corrections and filters that were traditionally applied during acquisition to now be implemented in the processing phase. As filtering becomes an optional post-acquisition procedure, it is crucial for processors and interpreters to understand the effects it can have on data and to make the best choices for specific applications. The number of filters and models included in the study are by no means representative of all options and environments, yet it is clear that significant data errors can be introduced if the only aim and measure of success is to provide smooth and visually appealing data. And finally, a data adaptive filter that applies filter widths inversely proportional to curvature shows promising results for providing visually appealing data with less error than other filters evaluated in the study. Thank you very much.
We have time for, thank you, Magno. We have time for questions. Yes.
Have you investigated the impact of filtering on inversions?
No, I haven't done that yet. I'm sure that's the next phase that will be very useful in the process. Maybe Andrea, you've done that.
Thanks, Magno. Yeah, we've done that on the Airborne IP, for example, which is going to be my next question for you. It is large. It's very large. So you can have the same data set giving very different answers depending on how you filter the data and how you process it. She knows earlier on, because it was very nicely proven here. Yeah.
Thank you. One more question, please.
Hi, Magda. Nice to meet you from your phone after a long time. So we started using these spatial filters for our item data, especially to remove the high frequency power line noise.
Yeah.
So, but surprisingly, when I see your slide, we don't see any reduction in the amplitudes, and all the amplitude scales remains the same. But what we have observed is there is a significant reduction in the amplitudes of your signals of all the channels. And once we add this percent, and when we use this data for this inversion. So what we observed is we lost a lot of details in the data, especially using these spatial filters. Of course, better that we use your MOA filter that would be not to us.
Yeah, I think, yeah, and Andrea is probably once again better to answer this than me. I'm not that involved with inversions, but when you do an inversion, you force the program to fit your model data to the actual data. If your data that you get is 1,000 times less accurate when fitting it to your model data, the filter data is less accurate or less close to your model data than your unfiltered data is, you will get an answer that is very different. And it might look smoother, it might have higher precision, but it will have a lot less accuracy. And we have to decide what is most important.
Any other questions? Andrea.
Bill, I've been working with Airborne IP, and I'm really looking forward to having a filter that helps processing Airborne IP affected data in an effective way. So I was wondering, because with Airborne IP you have two things happening at the same time. It's late in time, it's low signal, and it has a very large curvature change, which is hell. So do you think that this mother role filters could have a role in that?
Yeah, so we've applied this to the spatial, but So what we've always done is we assume that in the late time we have smooth curvatures, but now with IP that's not the case anymore. So certainly applying this process of filtering data based on actual curvature in the data and not just this assumption that it is going to be smooth will make a difference for sure. We can work on that.
Really? Okay, Jim, one last question.
Just one comment. The solution is to filter your model with the same filter as filtering the data. That's the first pass. But you need to know what the filter was applied to the data to be able to apply to the model before you attempt to advance. So I believe it's better to fit noisy data to the model. And the best, least squares is a fantastic model of what's with noisy data.
Thank you. All right. Well, let's thank Magdal for her forward-looking talk. Actually.